Hey everybody, Mr. Judson here. So we need to talk about a third method to find the volume of a solid that is rotated around a line. And this method is called the shell method. And so first we need to understand what they're referring to. To me, calling it a shell method is kind of weird because I think seashells. But really it's a bunch of cylinders. Probably should be called the cylinder method. I don't know. But if you look at this picture, what this looks like is a bunch of cylinders wrapped around. This is the y-axis. They've kind of cut part of it out. And so what you do is you find the volume of each of these cylinders. Here's another picture. I've got it's not even a cylinder. It's the surface area of a cylinder. Think of it this way: if I have a Campbell soup can, there's a label on here, and if I took this label off, it's really just a piece of paper. There's the seam right there. If I took it off and unpeeled it, what I would have is a rectangle, and in that rectangle, it would look something like this. So imagine I cut that seam on the back of the can and started to unfold it, and eventually that would become just this rectangle. But the length of this side is really the distance around the can. That's the length of this edge of that rectangle, and that's just the circumference, which is 2 pi times the radius. This right here is just the height of that cylinder, which is the length of one side. And what we have to do is we've got to account for a little bit of thickness, and that little bit of thickness is what you see right here. Okay, the thickness is really the thickness of a sheet of paper. It's almost nothing. I could almost say that the cylinder method is really like this. If I take a whole bunch of sheets of paper and do something like that, eventually it gets thicker and thicker, and we get some volume to this thing. All right, and so as we look at this thickness, here's another one. I have to decide: am I going to call that a dx or a dy? And we'll talk about that here in just a minute. All right, so I'm going to go back to an example that we've already done. I'm going to take this region that's bounded by y equals x squared, just a parabola. Y equals 0, that's the x-axis, on the interval 0 to 2. And I'm going to rotate this about the y-axis. So if I did that, I would get another shape like this over on this side. And if I, kind of imagine rotating this around, it would be like a bowl on the inside. I guess on the outer part it would be like a cylinder. And so I could use the washer method for this. That would work. Occasionally there's times where the washer method doesn't work. And usually that happens when you subtract a function from itself. Okay, kind of like when we started using the dy. That's because we ended up with a situation where I was subtracting the same function from itself. And so when that happens, then you would have to use the shell method. But I could use either the washer or the shell method. Either one would work. Today I want us to really focus on the shell method so we understand it, and so we're going to force ourselves to use that. So what I'm going to do is I'm going to draw a cylinder here. There it is. This part down at the bottom we wouldn't be able to see. And then what I'm going to do is I'm going to give that cylinder a little bit of thickness. Now, even though this looks a lot thicker than a piece of paper, that's really the way we want to think of this, is we just want to think of it as one piece of paper that's wrapped around like this. And it has a little bit of thickness. Remember how we always say dx or dy is just a very small amount? Well, that's what we see here, a very small amount for that. All right, and so when I look at the thickness, what I want to do is I always want to go out to the farthest edge out, away from the axis of rotation, towards my original curve. And so when I look at this thickness right here, I think this is the hardest part of the shell method. I don't want to look at the thickness here. I want to go as far away from the axis of rotation as possible towards my original curve, and I want to think of that as the thickness. And because that's running in the same direction as the x-axis, I want to call that dx. If there's a spot where we struggle, that's going to be it right there. How do I decide on dy or dx? Okay, start at your axis of rotation, get as far away as you can towards the original curve, and think to yourself, what direction is that running? And it's running parallel to the x-axis. And so that's what I want. I want to call it dx. Sometimes people think, well, if you rotate around a vertical line, this will just be dx. If I rotate around a horizontal line, then I'll choose dy. That works too. All right, so I want everything to be in terms of x. So if you think about it, we said just a second ago that the area of this piece of paper, or this cylinder, is going to be 2 pi times the radius times the height. And what I want to do is I want to do an integral, a whole bunch of these, with respect to x. So what I'm going to do to start is I'm going to move that 2 pi to the outside because it's just a number. So I've got 2 pi times the integral from a to b, r times h, and then dx. This right here is our formula for the shell method. What I need to do now is I need to find an expression for the radius in terms of x and the height in terms of x. And I need my a and b values to be in terms of x as well. So to get your a and b values, let's go back and look at this picture here. This almost looks like this could be a parabola that was rotated around. Actually it is, it's just a more complicated one. But what you want to think is, where's the smallest cylinder going to be? It's going to be right in here, as close to the origin as possible, or the smallest shell. Okay? And your largest shell is going to be out here towards the outer edges. It'll go like this, kind of wrap around, and then do this again. So when you look at that, you want to say that the shells go from 0 to 2. Where's the smallest one at? And where's the edge of the shell for the largest one? Smallest one's at 0, largest one's at 2. So we've got an integral. It's going to be 2 pi times the integral from 0 to 2. And now I need an expression for the radius. So what I need to do is I need to start on my axis of rotation and go out to this point right here. And so the radius really is just whatever that x coordinate is. This is just from 0 to x, depending on where that cylinder's at. And whatever that x coordinate is at that time, that's going to be the radius. So I can just put in an x for that. And then here's the height. The height is going to equal a y value. Right? From the x-axis up to that point, that's just a y coordinate. And that's going to be the height. So I'm going to put times y and then dx. So yeah, we can look at that and go, well, that's a problem. I want everything in terms of x. So the question now is, what is y equal to? Right there, y is equal to x squared. And so what I end up with is 2 pi times the integral from 0 to 2 of x times x squared dx. So I guess really we could just call that x to the third power. So 2 pi times the integral from 0 to 2 of x cubed dx. That will give me the volume of that solid. So what is that? That's x to the fourth over 4. We're going to evaluate that from 0 to 2 and multiply by 2 pi. And so what I get is 2 pi times, plug in a 2, you get 2 to the fourth power, which is 16, divided by 4, that's 4, minus what you get when you plug a 0 in, that would just be 0. So my answer must be 8 pi cubic units. And I think we did this problem when we first started doing the washer method. You can go back and check the answer. You'll see it's the same thing that we got before. We're just using a different method, the shell method. All right, so you guys try this one. We've got an area that's bounded by a parabola, half as high as what's normal. Y equals 0, x equals 6, and we're going to rotate that region about the y-axis. You guys go ahead and give it a shot. Let's just draw the picture first. Want to make sure we get that right before we go through a whole bunch of work. So I'll give you just a second to do that. Okay, so I've graphed this region. I just went all the way out to 6 and said if I plug that in I get 36, half of that's 18, and so there's my height at that point. And we're going to rotate this about the y-axis, which means we're going to get another piece over here. And when we draw those shells, this is going to look a lot like our last problem. Here's one shell. And I'm going to give this a little bit of thickness to it. And so if I start at the axis of rotation and go back towards the original curve, this right here is going to tell me whether I want dx or dy. And I should choose dx. All right, you guys go ahead and set up the integral. All right, so we've got 2 pi times the radius, that's our circumference around, and then times the height, and we want everything in terms of x. So the smallest shell will be right here at the origin, going around the y-axis. The largest one will be out here at x equals 6. So we want this integral to go from 0 to 6. All right, the radius, again, if you look at this, it's from the y-axis out to this point, and that's going to be some xy coordinate, and the x coordinate would be that radius. The y coordinate at that point would be the height. So this is almost identical to the last one, it's just our equation is slightly different. So I've got 2 pi times the integral from 0 to 6. Radius is going to be x, the height is going to be y, and we want everything in terms of x, which means I still have to fix this piece. And right here y is equal to 1/2 x squared. So if I had 2 pi times the integral from 0 to 6, if this is 1/2 x squared, that means I've got x cubed over 2 dx. I'll just bring that 2 to the outside and divide, so what I get is pi times the integral 0 to 6 of x cubed dx. And so that's going to be x to the fourth over 4, evaluated from 0 to 6, times pi. And again, we're trying to find the volume. All right, so I plug in a 6. I do not know what 6 to the 4th power is. So 6 raised to the, to the 4th. That would be 1,296. So I got pi times 1,296 divided by 4, minus what I get when I plug a 0 in, which would just be that. If I divide this by 4, I get 324. So my answer must be 324 pi cubic units. All right, so here's another problem. This time we've got an equation that's a little more complicated. And we want the area that's bounded by this, y equals 0 and x equals 1, to be rotated about the line x equals 2. So first let's just try and get the graph, get the right picture, get that set up, and then we'll try and set up the integral. All right, so I just graphed this on the graphing calculator, and it actually looks like it's a little bit higher here than there is here. So there is a relative maximum and a relative minimum there. That right there would be a reason why I could not use a washer method on this, because I would end up in a situation where, you know, when I'm trying to do outer radius minus inside radius, we've got different spots there where they kind of overlap, like we get the same line going across, and so how does it choose the right point on the graph? So this would be a case where we would have to use the shell method. All right, so I'm going to rotate this around this line x equals 2. So I'll get another shape like this, and then something that goes down, and I don't know, something like that. All right, so after I rotate that around, I don't know what this would look like. Some kind of weird donut with a point in the middle. I don't know. But what I want to do is I want to draw a shell or a cylinder. And so I'm going to draw one like this. This would be a part that we could not see. We'll give it a little bit of thickness. And I have to go from the axis of rotation back to the original curve. And right there, that's where I'm going to have my thickness. So once again, it's running parallel to the x-axis. That means those are x values. So we want to call that dx. And so now you guys try and set up the integral. All right, so here's our formula. And I got to remember, I want to work with the original curve, not the one that showed up later because I rotated something. This is the original one here. So there's going to be a point right here on this curve. Imagine this point sliding along this curve right here up to this point. That's what determines the radius and the height of each of these shells that we're going to have. Some will be a little taller, some will be a little shorter. Some will have a larger radius, some will have a smaller radius. So first I want to find the radius here. And since it doesn't start on the x-axis, I got to think of this as this x value minus this one. Well, this x value never changes. It's always at 2. This one will change as this point slides along the curve. So we want to call that radius 2 minus the x value. And the height right here would just be whatever the y value is. All right, so what I've got is 2 pi times the integral. I'll get my a and b values in a minute. My radius is going to be 2 minus x, and my height is going to be a y value. So think to yourself, as I stack all these shells side by side, they're going to go from what to what? You got to think smallest value to largest value. So I'm not really sure exactly where this is at. What we need to do is we need to go back to the calculator and see where this, what the zero of this function would be. So I've got my graph here. I'll do F5. I'm looking for option 2 is 0. I know it's somewhere between -2 and -1. And as it turns out, it's at -1.466. So I'm going to store this number in alpha A. And to do that, I have to go back to my home screen. And then I'll just say XC. That's for X coordinate. When I hit enter, you can see I got the same number, -1.466. And I'm going to store that in alpha A. So now make sure and get as accurate of an answer as I can. So it's going to go from that value all the way up to 1. So my integral will be from A to 1. And the only thing I have to fix is I've got to get something in place of y. So again, I'm going to go back to my original equation. And I'm going to say this is 2 pi times the integral from A to 1 of 2 minus x times x cubed plus x squared plus 1 dx. And now we're ready to put that whole thing into the calculator. All right, so I got that entered into my calculator. I got 2 pi times the integral from A to 1. 2 minus x times this original expression with respect to x. And so the answer that I have is 36.535 cubic units. Again, as we're doing this, if you're looking at this going, oh my gosh, this isn't really making sense, you can watch it over and over again, right? We can rewind it, go back, listen to that again. But it's really important. We got to figure out expressions for the radius and the height in terms of wherever our thickness is, which in this case was x. All right, one last problem. This time we've got y equals the square root of x plus 2. The line y equals x, just a diagonal line through the origin, and x equals 0. That's what we're bounded by. I'm going to rotate that about the x-axis. All right, so you guys try and just get yourself a picture first. All right, so here's y equals the square root of x plus 2. Square root function's been moved to the left 2 units, so I moved the starting point back to here. Here's my line y equals 0, and here's the line y equals x. And so this area right here, we're going to rotate that about the x-axis. So when I rotate it this way, I will get another curve like this. So if you rotate that around, it almost looks kind of like a semi-hollow bullet, maybe. But this would be a situation where it would be probably hard to do this with the washer method because it's not hollow all the way through. All right, so to draw my shell, here's 2 sides. Trying to make this look like a cylinder. And I'll give it a little bit of thickness. And so when I look at that thickness, from the axis of rotation I have to go back to the original curve. This is it right here. So that means I want this equation to be in terms of y, since that thickness is running up and down. All right, so you guys see if you can go ahead and fill in this equation. 2 pi times the integral from a to b, radius times height, dy. All right, so I did a little work off to the side here. One of the things I have to know is what are the coordinates of this point right here. And so that's just where these two equations intersect. So I set them equal to each other. And I squared both sides, got this, moved everything over to the right-hand side. I wanted to keep the x squared term positive. And then I factored that. And so what I'm going to get is x equals 2 or -1. Well, they don't really intersect at -1 because this graph doesn't rotate around to make a sideways parabola. So the only place they really intersect is at x equals 2. So that means y also equals 2. So this is the point 2, 2. And that's important because when I try to figure out the boundaries for my integral here, you know, my smallest cylinder is going to be wrapped around the x-axis, real tight like a straw. And the larger cylinder will be out here at this point. That'll have the biggest radius. All right, so if I think in terms of y, where are these cylinders going to be? The smallest one will be at y equals 0. The largest one will be at y equals 2. So this is going to be 2 pi times the integral from 0 to 2. Now I got to figure out the radius, and that's not too bad. If I just go straight up to, let's say, this point right here, the radius is just going to equal whatever that y value is, that y coordinate on this point. Okay, from the x-axis up to that point, that's how you measure a y value. And so there's our radius. The height is going to be a little tricky. So remember, I've got to work with the original equation, which is above the x-axis. And to get the height of this is running parallel to the x-axis. So I have to think to myself, I want the larger x-coordinate minus the smaller one. So this x-coordinate goes to the line. Let's just call that x sub 1. Minus this x-coordinate, which this is part of the square root function. I'll call that x sub 2. And so what I want is the larger x value minus the smaller one. So the height is going to be x sub 1 minus x sub 2. That's going to give me this height right here. Well, x sub 1 is just equal to y, and I need to get this in terms of y. So I've got my y value here. For this equation, if I want to solve for x sub 2, I'm going to square both sides, and then I'll move this 2 to the other side and subtract it. So what I'm going to get here is x sub 2 is equal to y squared minus 2. There's the expression that's going to give me the height of that function. So I'm still not sure this makes a whole lot of sense. The height, remember, is this x-coordinate minus this x-coordinate. Which, when I solve for these two x values, I'm going to get y minus y squared minus 2. The reason this works is because the y coordinates are the same for both of these. And so therefore, if I plug them in, it'll give me those x values to make sure and get the correct height. All right, so what I have now is y. I'll distribute this negative sign, so I get minus y squared plus 2 dy. And that's okay. You know, if we don't have to multiply this whole thing out. I suppose you can if you want. But if you're just going to throw it in the calculator, you might as well leave it just like this. Okay? So here's what I get when I put that into the calculator. So I've got 2 pi times the integral of y times, in parentheses, I've got y minus y squared plus 2 with respect to y from 0 to 2. All right, so when I put this into the calculator, I got an error message, and the way I fix it is I put a multiplication sign between y and this set of parentheses. And once I did that, it worked fine. The answer I got was 16 pi over 3. Cubic units. Had I distributed this y, maybe that error message wouldn't have happened. I don't think it would have. And so that might have been a good idea. But if you don't put a multiplication sign here, it kind of confuses the calculator a little bit. All right, so there it is. That's what we have for today. We're going to do number C5, our 5th assignment while we're out, page 472. And we'll do problems 1, 5, 9, 13, 21, and 25. I'll have a little information about Central Washington on our next lesson on Thursday. I will tell you guys, I'm a little concerned about one thing, and maybe people were gone on vacation over spring break. I just sat here at my house. But anyway, not as many views on the videos. I hope that's the reason why, and I hope that picks up. What I really hope is that none of us are thinking, you know, because the governor canceled school, we're done for the rest of the year. We're not done. We've got a lot of stuff to do. You know, we still have to worry about our Central Washington credit. I still don't know all the answers to everything, but I'm trying to work on that. So anyway, please do not think this is optional work. We need to do this, you guys. All right, take care of yourself. See you on Thursday.